So welcome to the first Form 4 topic known as Matrices and Transformation. Here we are combining two topics and see how they relate. So you have covered matrices in Form 3 and you have covered transformation in Form 2. So we are going to combine. So this topic, you must have covered a topic known as matrices in Form 3. Or in your area lessons. If you have forgotten, check on my videos on matrices, especially on multiplication. So what is transformation? A transformation is a change in position, size, shape of an object. For example, when we refract an object, it changes position. When we rotate, it changes position. When we enlarge, it changes in size. When we translate, it changes in position. So you have covered this in Form 2 on topic known as transformations. Now, in this topic, which is the first Form 4 topic, we are going to learn transformation represented by various matrices. So you are all welcome. To help us understand all about matrices and transformation, we are going to use an example. We will take a triangle, which is, we can give its coordinates. We have triangle, we have A. Triangle A, the point A, the coordinates are 4, 3. Then we have B, which has a coordinate 4, 1. And we have C, which has a coordinate 2, 1. So this is a triangle that we can plot on our graph paper we have here. So we can do that. We say this is can say this is 1. This is of course 0. This is 2. This is 3. This is 4. Then on the y-axis, we can say that is 1. We say this is 2, this is 3, this is 4, and remember to always label your axis. So this is our x. From there, we can plot our triangle and say our point A is 4, 3. So you come here, 4, 3 is positioned there. Our point B is 4, 1. So we put our point there. And our point C is 2, 1. So this is our point A, this is our B, and this is our C. We can now join the points to come up with our triangle. So this is our triangle ABC. We have plotted that triangle. Then we are saying we premultiply. We are going to premultiply the position vectors, which are 2 by 2 order of matrix, by another matrix which we are calling A is equals to into bracket minus 1 0 0 1, which is a matrix 2 by 2 matrix, and observe what happens. So when I talk of 2 by 2 position vectors, I'm saying A, or what we call OA, is equals to, we just write this in column form, and that will give us 4, 3. So that is what we are referring to as 2 by 2 matrix. So we write the 3 of them. So here we have another position vector OB is equals to, this one you write it is 4, 1, and you put the bracket. Then we have OC is equals to, you write this is 2, 1. By multiplying, we can multiply the 2 by 1 matrix by 2 by 2 matrix. We will start with OA. So we write it like this. You say we have a new A. So we have a new vector OA, which is equals to, we write our matrix here, which is a 2 by 2 matrix, which is minus 1, 0. We have 0, 1. and we multiply by OA, which is a 2 by 1 matrix, which is 4, 3. So when you multiply like that, this is what I mean by multiplying. We start multiplying we start with our matrix, then our column vector of OA. And that is why I mentioned that you need to revise the multiplication of matrices, because this is what you'll be dealing with in this section. So we multiply, we are going to multiply this. We multiply minus 1 times 4, that will give you minus 4. 0 multiplied by 3, that will give you 0. So it means here up here we have minus 4. Then we have, we are through with that row and column. And then we have 0 times 4, that is 0, plus 1 times 3, that will give you 3. So this will give us 3. Since O is our new position of A, then the coordinates of A prime, that is the image of A, will be minus 4 and 3. So that is our new position of A. We do the same to the other. Matrix. So we have O and the new B is equals to, then we have minus 1, 0, 0, 1. You multiply by 4 and 1. So this is equals to minus 1 minus 1 times 4, that will give you 4, plus 0 times 1, that will give you 0. So we end up with minus 4. Then we have 0 times 4, that will give you 0. 1 times 1 will give you 1. So the new position of B, that is our B prime, is equals to the coordinates, that is, we want to write that as a coordinate. So this will be our B, which is 4 and 1. Those are the new coordinates of B. So we go to C, we do the same. Then we have C. We can say C is going to give us the new position of C, that is OC, is equals to minus 1, 0, and 0, 1. We multiply by the position vector of OC, which is 2, 1. So when you multiply that, you are going to get minus 1 times 2, that is minus 1 times 2, that will give you 2. 0 times 1, that is 0. So you end up with minus 2. Then we have 0 times 2, that will give you 0. And 1 times 1 will give you 1. So you add 0 plus 1, you get. So our new position of C, that is C prime, will be minus 2. We have minus 2, 1. Let us now plot the new triangle and see what happens. What has happened to our object. This is our object. That's our object and our image. So A, okay, let's modify our coordinates. We will say we have now negative. So this is minus 1, minus 2, minus 3, minus 4. And then the y side we have minus 1, minus 2, minus 3, minus 4. Now our image, we have A is minus 3, minus 4, 3. So minus 4, 3 is there. So this is minus 4, 3. This will be our new position of A. Then we have B is 4, that is minus. Here we have minus 4, 1, minus 4, 1. That will be our new position of B. And we have our C, which is minus 2, minus 2, 1. So that will be our C prime. So we join the 3 points to come up with our triangle. Now this is our new triangle. which we call the image of our triangle ABC. Now, if you observe the two triangles, what has happened to this triangle? We can clearly see that we can obtain our object, our image, by reflecting the object through the line x is equals to 0 or the y-axis. This is the y-axis. So if you reflect here, you can see, if you count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It is a reflection through the line y-axis or x-axis or 0. Now, this is where we conclude. Then it means our matrix, which is here, this matrix here actually represent transformation, which is a reflection of through the line y-axis or the line x is equals to 0, and that is the objective. That is what we wanted to achieve. So we are going to do several examples to see the kind of transformation represented by various matrices. So let's look at another example. So before I tackle another example, I want to make a conclusion here that from the two diagrams, BC, that is ABC, our object, can be obtained if triangle ABC, that is our object, is reflected through the line y-axis or line x is equals to 0. This means that the matrix that we had, which is A, which is up here, actually represent reflection in the line x is equals to 0. And then from there, you can see now we have combined. Here we have a matrix representing a transformation. So let's move to the second example and see whether we'll be able to get another matrix that represent another transformation. So this is our example 2. We are told to identify the transformation represented by the matrix 0, minus 1, 1, 0. Use triangle P, 1, 2, Q, 3, 2, and R, 3, 3. Now, what we do here is we are going to pre-multiply our matrix with the matrix that will form with the column vectors of our points of the triangle PQR. This time I want to do it a bit different. I don't want to pre-multiply the matrix with by individual column vectors that are formed by the point P, Q, and R. I want to combine them. So this is how I'll go about it. So this is our matrix that we are supposed to pre-multiply, and that is 0, minus 1, and 1, 0. So that is our matrix. Instead of writing individually, I'll write like this. So this is 1, 2, that is for P. This is 3, 2, that is for Q. And we have 3, 3 for our R. So what this means is that this is our P, this is our Q, and this is our R, so that it is easier for you to multiply. So this will give us 0 times 1 is 0, minus 1 times 2 is minus 2. When you add, you'll be able to get minus 2. Then 0 times 3 is 0, minus 1 times 2 is minus 2. So that you also, when you add, you get minus 2. Then we have 0 times 3, that is 0, minus 3 times 3, minus 1 times 3, that will give you minus 3 when you add 0 and minus 3. Then we come to the second row. 1 times 1 is 1, 0 times 2 is 0, so 1 plus 0 you get 1. 1 times 3 is 3, 0 times 2, that is 0, so when you add, you get 3. 1 times 3 is 3, 0 times 3 is 0, so 3 plus 0, you get 3. So what this implies is that these are our new images of P, Q, R. So we label P prime, Q prime, and R prime. So once you have that, then we can now get the coordinates of our new image. That is, we have P. P is 1, 2. It is transformed to our P prime, which is minus 2, 1. Our Q, the coordinates of Q are 3, 2. After multiplying, we get the image of Q, which is now this one, minus 2, 3. And finally, we have our R. The coordinates of R are 3, 3, as we had been given. It is transformed to the image of R, which is now minus 3 and 3. Now what we do is we are going to plot the two triangles and observe what has happened to our triangle PQR, so that we get the image of our triangle P prime, R prime, and Q prime. So let's plot the two triangles. So we are going to use this graph paper to plot the two triangles. So let's say this is where we have our 0 or starting point. So here we can label our x-axis 1, 2, 3, 4. That is our x-axis. Our y-axis, the other side we have minus 1, minus 2, minus 3, and minus 4. So that is the x-axis. The y-axis we have 1, we have 2, 3, 4, 5. Maybe that's enough. For you to be able to know how you label your axis, you need to look at the coordinates here. You can see the value of x is not going beyond 3. The value of y is not going beyond 3. On the other side, only the negative, only the x has negative. We don't have y negative values of y, so that is why I have not concerned myself with the negative side of the y-axis. Now we plot. Our P is 1, 2, so that is where we have our point P. Our Q is 3, 2. Our 3, 2 is there. So that's where we have our Q, and our R is 3, 3. So we have we have R. So let's plot. Let's join the 3 points to come up with a triangle. So this is our triangle PQR. From there, we are going to plot the triangle P prime, Q prime, and R prime. So our P is this one, which is minus 2, 1. That's where we have minus 2, 1. So that is our image of P. Our Q is minus 2, 3, minus 2, 3. That is where we have our Q, and our R is minus 3, minus 3, 3, minus 3, 3. Let's change our position of Q. So minus 3, 3 will be there. So that is where we have our R, the image of R. So we are going to join the 3 points to come up with a triangle. So that is a triangle of our image. And if you look at our triangle here, which is our object, the one that we started with, and its image, you can see there is a transformation that has happened. And we can interpret this by saying, if you rotate this triangle, the positive quarter turn, that is positive 90 degrees, positive 90 degrees rotation, and clockwise is what we call the positive rotation, you will be able to get our image there. So we can conclude by saying that our matrix 0, -1, 1, 0 represent a positive quarter turn as a transformation, and that is what we started with. We say that we want to relate the transformations represented by a matrix. The first one we saw, it is the matrix represented with our first example. The matrix represented a reflection through the line x is equals to 0. This matrix represents a different transformation, and that is a positive quarter turn. So the conclusion of this example is that the matrix 0, -1, 1, 0 represent a positive quarter turn about the origin, i.e. a rotation of positive 90 degrees about the origin. So this is our third example. We are required to identify transformation represented by this matrix, that is 0, 1, 1, 0. Use triangle P1, 2, Q, 3, 2, and R, 3, 2, 3, 3. Same triangle that we have used in our last example. So let's start by multiplying our matrix with the column vectors of our triangle. So this will be, we say it is 0, 1, 1, 0. We multiply by the column vector formed by PQR will be 1, 2, will be 3, 2, and also we have C, which is 3, 3. We close the bracket. So note here that this is our P, this is our Q, and this is our R. So after doing that, we now multiply and we will get this is 0 times 1 is 0, 1 times 2 is 2, so 2 plus 0, you get 2. Then we have 0 times 3 is 0, plus 1 times 2, which is 2. Then we have 0 times 3 is 0, 1 times 3, you add, you get 3. We come to the second row. 1 times 1 is 1, 0 times 2 is 0, so 1 plus 0 is 1. 1 times 3 is 3. 0 times 2, you get 0, so you end up with 3. 1 times 3 is 3. 0 times 3 is 0, so 3 plus 0, you get our matrix. So note, this is the image of P, the image of Q, and the image of R. This means that the transformation that has taken place, we had our P, which has a coordinate 1, 2. It is transformed to our image of 2, which is P prime into bracket 2, 1. Then we have our Q. The coordinates of Q are 3, 2, 2. They are transformed. It is transformed to Q prime, which is our Q prime, whose coordinates are these ones, 2 and 3. Close the bracket. And finally we have our R, whose coordinates are 3, 3. It has been transformed to R prime, which has a coordinate 3, 3. Now, with that, now we should plot the two triangles so that we are able to find out what transformation is represented by this matrix. So this is a graph paper that we are going to use to be able to to plot our two triangles. So we go ahead and label our triangle. Because all the values are positive, we just make use of this the left bottom corner. So we have 1, 2, 3, 4. Remember always to label your axis. So here we have y-axis is 1, 2, 3, 4, 5, 4. That's okay. So we start with our P. P is 1, 2. So 1, 2. This is where we'll find our P. Then so we label that. Our Q is 3, 2. Our Q is 3, 2. So this is where we have our Q. And then we have our R, which is 3, 3. This is our R. Now we are going to join the 3 points to come up with our image. So that is our triangle PQR. So from there, we are going to plot the image of this triangle by using the coordinates of what we have obtained. So our P prime is 2, 1. So 2, 1, we are going to use a different color. So that is our image of P. And then we have Q prime, which is 2, that is 2, 3. 2, 3 is there. So that's why we have our Q prime. And then we have our R prime, which is 3, 3. So our R is just on the same place with R. We are going to join the 3 points so that we can be able to get our triangle. So that is the triangle that you get from our images, PQR prime. Now, since we are required to identify the transformation represented by this matrix, then you can see here is our P and where P is. If we draw a line of x is y is equals to x, that line passes through here. So let's plot that line. So that is the line of y is equals to x, and you can see that this is actually a reflection of P is reflected through the line. This is the line y is equals to x. You can see Q is reflected to the other side, and because the point R and its image lie on the line, they are at the same point. So this means that our matrix here represent a reflection through the line y is equals to x. Let's conclude. So in my conclusion, I will say that this matrix of 0, 1, 1, 0 represent a reflection through the line y is equals to x. So that brings us to the end of our lesson, and I hope you have understood what our objective was, that we wanted to show that a matrix can represent a transformation. Now, I'll have worked so many examples to supplement. So if you don't understand, go through the examples that I'm going to post. Written example 4, 5, 6 on transformation and matrices, lesson 1. So I hope you have enjoyed the lesson, and I hope you have understood what I wanted to teach to you today. So welcome to the second lesson, and check on many examples that I'll be posting in this media. Finally, for any queries, you can contact me, Teacher Wamta. My number is that one, 0725357594. You can also get me in WhatsApp you can email me. I have a website, teacherwamtaaniacademy.com. You can also get me in Facebook. I offer one-on-one online teaching. I also train those who would like to make such videos so that they can make some income, and any other education related issue that I may be assist. So welcome to other lessons. So this is our second lesson in the topic matrices and transformation. In this lesson, we will learn how to get a matrix of transformation given the object and the image. So we are going to do that using an example. We are told that we have triangle ABC and the vertices are A 2, 5, B 2, 2, and C we have 4, 2. Its image had A prime, which is minus 4, 10, minus 10. The other one is minus 4, that is B prime. And the C prime is minus 8 and minus 4. So we are supposed to find out the matrix that transformed triangle ABC onto triangle A prime, B prime, and C prime. So we are going first of all to plot the two triangles. Then from there we identify the matrix that was used to do the transformation. So this is a graph paper that we are going to use. We are going to plot the two triangles on this graph paper. So let's say this is 1. We start from here. Here we have 0, we have 2, we have 4, we have 6. On the negative side we have minus 2, we have minus 4, we have minus 6, minus 8, minus 10. Then that is our x-axis. Y-axis, we say this is 2, this is 4, that is y-axis. The negative side we have minus 2, we have minus 4, we have minus 6, we have minus 8, we have minus 10. Let's start with our object. This one, our A is 2, 5, so we take 2 there. Our 5 is there, so that is where we have our A. Then we have our B, it is 2, 2. So this is where we have our B, which is our second point. Then we have C is 4, 2. 4, 2, that is where we have our C. So that is a triangle that the image, the object. So let's first of all plot that triangle. Then we go ahead and plot the other triangle, the image. So this is a triangle that we have been given, the object. So let's go ahead and plot the image. A is at minus 4, minus 10. So that's minus 4, and this is minus 10. So minus 10, 4 minus 10, that's where we have our point. So this is the image of A. Then B is at minus 4, minus 4. So our B will be there. So that's where we have our B prime. That is the image of B. From there we have the image of C, which is minus 8, minus 4. Minus 8, minus 4. And this is where we have an image of C. Then we join the 3 points to come up with a triangle, which is the image. Now this is a triangle, the image of that triangle under a certain transformation. And by observing, you can say this is an enlargement. if you count the number of the rank of AB, that is 1, 2, 3, 4, 5, 6. AB here it is 1, 2, 3. So the rank of BC, it is 1, 2, 3, 4. BC, it is here, it is 2. So the triangle has been enlarged twice, but the center of enlargement is the origin, that is at 0, 0. At 0, 0, that is where we have the center. So the enlargement scale factor is -2. Minus meaning that if you draw the triangle has been enlarged on the opposite side of the center of enlargement, which is the origin. If you draw lines from A to A prime, you find that from A to the center is half the length from the center to the A prime, and the same case applies to B prime and B and C prime. So that is how we determine. So this is the enlargement scale factor is equals to 2. So, but we still don't know the matrix that was used to transform, to make, to enable this transformation to take place. So that is what we are going to do. So this is enlargement. From there, for us to be able to get the matrix that was used to transform this, we are going to say that let our matrix be A, B, C, and D. Then if we are able to get A, B, C, and D, then we will be able to get the matrix of transformation. Remember what we said in our first lesson. For we multiplied the matrix by the matrix formed from the object. So we are going to multiply this by 2, 5. That is the column vector of A. Then here we have 2, 2 for B, and we have 4, 2. When you multiply that, what is supposed to give you is the matrix formed from the column vector of the image. So this is -4 and -10. Then we have -4 and -4. Then we have -8 and -4. And this is A, B, and C. And this is A prime, B prime, and C prime. So if we are able to get A, B, C, and D, then we have obtained the matrix of transformation. We multiply this just the way we multiply we multiplied matrices. So we say A times 2, that is 2A, plus B times 5, that will give us 5B. So that is our first column. Then A multiplied by 2, that will give us 2A. We add to 2 times B, that will give us 2B. Then we have A multiplied by 4, that will give us 4A, plus B times 2, that will give us 2B. So that is the first row. We come to the second row. We said C times 2, that will give us 2C. Then we have plus D times 5, that will give us 5D. So C times 2, that will give us 2C, plus D times 2, that will give us plus 2D. Then finally we have C times 4, that will give us 4C, plus D times 2, that will give us 2D. So that is one matrix. So we close this bracket. This matrix is equals to this matrix. So we have -4 minus 4, minus 8, and then we have minus 10, minus 4, minus 4, and we close the bracket of the matrix. Now, when we were running matrix, we said that because these two matrices are equal, we have an equal sign. Then what we normally say is that the corresponding elements of the matrix are equal. That is 2a plus 5b is equals to minus 4a, and 2a plus 2b is equals to minus 4. That is 2a plus 5b is equals to minus 4, corresponding elements of the matrix. Then 2a plus 2b is equals to minus 4 again. Now we want to eliminate these two forms a simultaneous equation, and we solve them by eliminating a, because we have 2a and 2a, we minus. So 2a minus 2a is 0. 5b minus 2b is 3b is equals to minus 4 minus minus, that changes to positive, so that will give us minus 4 plus 4, which is equals to 0. Divide both sides by 3, implying our b is equals to 0. If b is equals to 0, then you can substitute here in this one equation and say, since b is 0, then 2a is equals to minus 4. 2a is equals to minus 4. Divide both sides by 2, implying our a is equals to minus 2. Fine. So we have managed to get the values of a and b. So let's go ahead and again work the same and get the value of b, c and d. So just like we have done with a and b, we also equate this expression to the corresponding element, which is minus 4. So we say it is 2c plus 2d. We are equating 2c plus 5d is minus 10. That is this expression here, and we equate it to corresponding element, which is minus 10. We also do the same to 2c plus 2d is equals to the corresponding value is 4 minus 4. So we close the bracket. We solve these two equations simultaneously. So we subtract 2c minus 2c is 0, 5d minus 2d is 3d. Then we have minus 10 minus minus 4, that will give us minus 6, because minus 4 will change to positive. So we divide both sides by 3, and you find that d is equals to minus 2. So once we get d, we substitute here. So we say 2c plus, now d is minus 2, so it is 5 multiplied by minus 2, that will give us minus 10. So we change that to minus. We say minus 10 is equals to minus 10. We take 10 to the other side, we get 2c is equals to 0. 2c is equals to 0. Divide both sides by 2, and c is equals to 0. So we have obtained the three values that we needed, and that is a, b, c and d. Now, since we had defined our transformation matrix as a, b, C and D, this one, then what we do is we say A, B, C and D, that is our transformation matrix, is equals to, we found our A is minus 2, we found our B is 0, that one, so A, B, that is, we have, that is 0. Then we found our C, we have found our C is 0, so, and our D, we found it is minus 2. So this is the transformation matrix that was used to transform this figure to this triangle, which you can see even the matrix is telling you. You can see we have minus 2 there. So that is what we defined as our enlargement scale factor. We said it is negative because it is enlarged on the opposite side of the center of enlargement, which is the origin. So that is how you work out that. So remember, you need to define your, to give your matrix letters. You can give any letter so long as you are able to follow. You can use A, B, C, D, A, B, C, and D. You can use M, N, R, S, anything that you like as long as. Then once you are able to pre-multiply and you equate the two matrices which you form from the object and the image, you'll be able to form equations which you solve simultaneously like that. Then you'll be able to get the values of the elements of the matrix that are used to transform the object. So that is how we get the matrix of transformation given the object and the image. So we are going to do several examples so that you understand how to go about it. So this is our example 2, whereby we are told the following diagram shows a triangle ABC whose vertices are 1, 0, B, 3, 0, C, 3, 3. The triangle A prime, B prime, C prime, whose vertices are A prime, 0, 1, B prime, 0, 3, and C prime, minus 3, 3, is an image of ABC after a translation. I describe the transformation and its matrix. So the first thing we do is we look at, we observe our two diagrams. So this is the image, this is the object, and this is the image. If you look at A has been transformed from this point, that is 1, 0, to 0, 1. You can see that this is a rotation. The same case applies to B. It has been rotated through a positive 90 degrees. So transformation is a positive 90 rotation about the origin. In which we are saying this is our origin at point 0, 0. Now from there we are required to find the matrix of transformation. That is a matrix that you can use to transform this figure onto our image. Now for us to do that, I said in the beginning, let our transformation matrix be A, B, C, and D. So that is our transformation matrix. Then we say that if you multiply with the column vectors of our object, which will form a matrix, you should be able to get the matrix formed from the column vectors of our image. So the matrix that will be formed is 1, 0, we have 3, 0, we have 3, 3. So that is a matrix formed from our our object. It should be equals to the matrix formed from the image, and that will be 0, 1, and then we have 0, 3, then we have minus 3, 3. So that is the matrix. So what we mean here is, this is our A, this is our B, this is our C, this is our A prime, this is our B prime, and this is our C prime. So if we will be able to get the values of A, B, C, and D, then we have obtained the matrix of transformation. So we multiply. A times 1 is A, B times 0 is 0. So here you have our A. Then A times 3 is 3A. B times 0 will be 0. So that will give us 3A. Then A times 3, that will give us 3A plus B times 3 will give us 3B. We come to the second row, which will be C times 1, that will give us C. D times 0, that is 0. So here we will be left with C. Then we have C times 3, that is 3C. D times 0, that will be 0. So this will have 3C. Then we have C times 3, that is 3C. Then we have plus 3D. So we close the bracket, and that should be equals to our matrix of the object, which is 0, 1, 0, 3, minus 3, and 3. So from there, you look at our A and B, C, and D. From our matrix, we can clearly say that these two matrices are equal, and therefore the corresponding elements are equal. Therefore, our A, which is here, is equals to 0. So that is direct. A is equals to 0. What about our C? Our C is equals to 1. So we already got C is equals to 1. Now, we say 3A plus 3B is equals to minus 3. And we already know A is equals to 0. So this will mean that 3B is equals to minus 3. Divide both sides by 3. Divide by 3. This means implying that our B is equals to minus 1. So we are left with D. We have already said that our C is equals to 1. So this is 3 times 1, that will remain 3, plus 3D is equals to, this part here is equals to 3. So we take 3 to the other side. We have 3D is equals to 3 minus 3 will give us 0. Divide by 3, both sides divide by 3. It means our D is equals to 0. So we have managed to obtain the 4 values. That is, our A is equals to 0, our B is equals to minus 1, our C is equals to 1, and our D is equals to 0. So we write A, B, C, and D, which was a matrix of transformation which we had defined, is equals to 0. Our B is minus 1. Our C is equals to where is our C is equals to 1, and our D is equals to 0. So that is a matrix of transformation that was used to transform this object onto the image of this one. So that is how you work it out, and it is very easy. So we look at one more example. So this is an example of our continuation of matrices and transformation, lesson 2. And this question we want to find the matrix of transformation. So we are told that we have a triangle AB, which we have A prime, so given the vertices, we are required to find the matrix of transformation. So for us to be able to do, we say let's assign the transformation as A, B, and D. From there, then we will multiply this by the matrix formed from the vertices of the image, and 5. Then we have 9 minus 4. Then we have 8 minus, and we close the bracket. When you do this, it is formed by the column vector of minus 4, 5, and minus 3, minus. Remember, this is B and C. This is A prime, B prime, and C prime. So we say A times 5 will give 5A. Then we have B times 4, that will be minus 4B. A multiplied by 9 will get 9A. B multiplied minus 4 will be minus 4B. So you have 9A minus 4B. 8 times 8, you have A. Then B times might B. We come to the second row. Times 5 will give us 5 minus 4D. We have done with the first row. So give us C minus 4. Give it C minus 3. This matrix is equals to our matrix here, which is formed by the vertices of the image, and this will be minus 4, 1, minus 4, minus 5, minus 3, minus 5. These two matrices are equal. We have the line responding are equal. 5 minus is equals to 4, and 9 minus B is equals to 4. Let's start with the 9 equals to 5A minus B equals to, this is the same as minus 4. From there, these are linear, and we can simultaneously. So we are going 2 from equation 1. We make a, and that we say 9 minus 5A give us minus 4B will give us minus 4 plus B, which is equals to is 4 minus 4 give us 0. Divide both sides by, we divide by 4, find A is equals to 0. After 5 is equals, we can come and substitute here and say 5 minus 0. 5 times 0 is 0, so minus 4B is 0 minus both minus. So this here, this given, so is 1. So we know values of A and B. Back to our matrices. So this element of it, so is C minus is equals to minus 5. We have the equals to minus 1. These are linear equations. We also eliminate. So 9, we don't add, but Let's subtract. We eliminate 4D minus C will give us 4 minus C will give us 0. That is equals to minus will give us minus. Divide both by find that minus. After finding, we substitute this will be in this here minus, that is 5, so we say minus 1 not 5 times 5 in D equals to minus. We take side positive, so minus 4D is minus 1 plus is equals to minus 4D equals to 4 divided by minus. You find that D is minus. Have a matrix of value. So A is D 2 0, or B is minus 1, D is minus 1, D minus matrix of transformation. So we have come to the end of our second lesson, that is finding the matrix of transformation. But before we wind up, it is important to note that under any transformation represented by a 2 by 2 matrix, 2 by 2 matrix is where we have 2 rows and 2 columns, like 1 0 0 1. That's a 2 by 2 matrix. The origin does not change. If the transformation is a rotation, then the origin, it is about the origin. If it is a reflection, the line of reflection passes through the origin. So that brings us to the end. I hope you have understood. I'll be posting more examples relating to this lesson 2, that is finding the matrix of transformation, so you can understand more about it. Do more exercises from your textbooks and you'll be able to get the points that we have emphasized in this lesson. The unit square in the topic matrix of transformation. So welcome to the third lesson of our topic matrices and transformation. In this topic we are going to deal with the unit square. So what is a unit square? A unit square is a 1 unit square, simply as that. We have a figure here which is a square. So we can say this is 1 unit and this is 1 unit. So that is what we call a unit square. So it could be 1 centimeter, 1 meter, that is still a unit square. So we are going to present the unit square on the Cartesian plane and see how we use it in this topic to determine the matrix of transformation. We are going to use this graph to plot our unit square. So we will take that as the origin. Let's take this is our y-axis and this is our x-axis. So we can have this is 1 and this is 2 along the x-axis. This is 1 and this is 2. So we have defined a unit square as a square that has 1 unit in dimension. So let's take that is for along the y-axis, here that is 1 unit, along the x-axis that is 1 unit, and here we have another point. So those 4 points plus the origin forms the unit square. So this is our unit square. We are going to name the vertices of our square. So this we are going to give it I, capital I. This we are going to name it J, and this we are going to name it K. So we have the vertices, and of course we have the origin. So we have O, which is the origin. The coordinates of the origin obvious is 0, 0. Then we have I. The coordinates of I is 1, 0, 1, 0. And the coordinates of J are 0, 1. And the coordinates of K are 1, 1. So this is 1, 0. This is 1, 1. This is 0, 1. And of course we have the origin. So those are the coordinates of a unit square. So we are saying that the vertices of I, which is 1, 0, and J, when written both in column form, makes an identity matrix. We utilize the properties of an identity matrix to help us identify the matrix of transformation. So here we have, this is our I. So I can be written as 1, 0 in column form, and the J can be written as 0, 1. We put the bracket. So you note here that this is an identity matrix, whereby this is our I and this is our J. So in conclusion, the unit square help us to easily identify the transformation represented by a given matrix. It also helps us to obtain easily a matrix for a given transformation. Why are we saying easily? Because in our earlier lesson, we saw that for us to identify the matrix of transformation, we had to get a triangle, pre-multiply the image, the matrix and the image that we had to get the object. If you are given the image and the object, you have to do some multiplication for you to be able to identify the matrix of transformation. So we are going to see that clearly in our following example. So our example 1. Find the image of I and J under the transformation matrix 3, 0, 0, 1. As you remember earlier, for us to get the image, we pre-multiply the transformation matrix by the matrix that is formed from the coordinates of our object. So if we take, this is our I, the coordinates of I are 1, 0, and the coordinates of J are 0, 1. So from there, then we can form the matrix of I and J. So we have, this is 1, 0, and 0, 1. So this is I, and this is our J. Now, this is now matrix formed by the object, that is of the I and j, which are part of our unit square. So for us to get the image of the unit square using this transformation matrix, we write, then we have our transformation matrix, which is 3 0, and we have 0 1. We multiply by the matrix of our object, which is 1 0 and 0 1. When you multiply that, you note that this is an identity matrix, and whenever we multiply anything by identity matrix, it is like multiplying by 1. It doesn't change. However, let's multiply and see what we get. 3 times 1 is 3, 0 times 0 is 0, so 3 plus 0, we end up with 3. Then 3 times 0 is 0, 0 times 1 is 0, 0 plus 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 0 plus 0 is 0, 0 times 0 is 0, 1 times 1 is 1, so 0 plus 1 is 1. So you note here that our transformation matrix has not changed. Actually, we can say that our image, this is our image of this is I prime and j prime are the same as the transformation matrix. Now, from what we have seen, the transformation matrix actually forms the image. So we can conclude, since I 1 0 and j forms an identity matrix, that is 1 0 0 1, the coordinates of the image are formed from the transformation matrix. Generally, the way I take it is that what has happened to the unit square will enable us to get the transformation matrix that has occurred. The following example is going to demonstrate very well how the unit square help us to get the transformation matrix. In our example 2, describe the transformation represented by 0 1 minus 1 0. Now, we know, we have learned that the coordinates of I are 1 0 and the coordinates of j are 0 1. They form an identity matrix, which is 1 0 0 1. So this is, we are going to use a unit square to help us identify the transformation represented by this matrix. So this is our object. So we pre-multiply with the transformation matrix, which is 0 1 minus 1 0, and our object is 1 0 0 1, which is an identity matrix. That means it doesn't change. We will still remain with our matrix here, minus 1, because it is like multiplying by 1. So what this means, that since we are saying this is our I and this is our j, the image of I is that 0 1 and the image of j is that. So we can make a sketch here and say what has happened to our unit square. So this is just a sketch, so don't worry about the straightness of the line. So this is x. So we take one unit here, that is 1, that is 1. So this is j and this is I. Now if we make the unit square, that is the unit no, that's not good. So this is we come down here, this is going to be our k. Remember, our coordinates of k are 1 and 1. Now I has been transformed. Our new I is coordinates 0 minus 1. So it is x is 0 and this is minus 1. So this is where we have our I, the image of I. The j prime coordinates are 1 0. So it means this is our new j. Now if we plot the If we plot this square, unit square, it will be like that. It's just a sketch. So this is the object and this is the image. So we can clearly see that the transformation here is a reflection through the line y-axis, or y is equals to 0. So we conclude that the matrix represents transformation. So it is a reflection through x-axis or y is equals to 0. So you can see very easily we have used our unit square to identify the matrix represented by this, the transformation represented by this matrix. So let's do another example. In our example 3, describe a transformation represented by matrix 0, minus 2, 2, 0. So we multiply our unit square with this matrix. So this means we have 0, we have minus 2, we have 2, we have 0. The units, our unit square, we have 1, 0, 0, 1. So remember, this is our I and this is our j. When you multiply that, you'll be able to get the same matrix as this one, because this is an identity matrix. So you have 0, minus 2, and 2, 0. So that is our image. So this means that this is the image of I and this is the image of j. From there, so we have our I, the coordinates are 1, 0. Our j, the coordinates are 0, 1. And our image, we have our I prime, we have the coordinates 0, 2. This is what we have obtained after multiplying the unit square. And we have a j, which will be minus 2, 0. So let's make a sketch of that and see what has happened to the unit square, which is going to give us the transformation represented by this matrix. Okay, this is the sketch I have. You can just use your hand to make that sketch. So this is where we have our I, and this is where we have our j. This is our k. The new image of j, of I, is 0, 2. So x is 0 and 2. So here is where we have the image of I. J is minus 2, 0. So this is where we have j prime, the image of j. Of course, now this is our image of k. If you observe this, you find that since this is our object, this is our image, what has happened to the unit square? It has been enlarged. First of all, if you reflect the unit square through the line y-axis, you get the first figure. Then you enlarge it, enlargement scale factor 2, you will be able to get this image. So we can conclude that the transformation is a reflection. We can say the matrix, this matrix here, represent a reflection in the line x is equals to 0 or y-axis, followed by enlargement, enlargement scale factor is 2. So that is what this matrix represent. So from you can clearly see that the unit square is very important in determining the unit, the transformation represented by a given matrix. If we are not to use the unit square, then we had a triangle. of triangle with formation matrix, then draw the figure, and then the transformation represented by that matrix. But you see here now, with our unit square, we are able to identify the transformation represented by the matrix very easily. Let's do another example. In our example 4, we are required to describe the transformation represented by our matrix, which is 0, minus 2. Then we have minus 2, 0. What we are going to do is to pre-multiply this with our unit square matrix. So we have 0, we have minus 2, we have minus 2, and we have 0. So when you multiply this 1, 0, 0, 1, you will get the same matrix. So it is 0, minus 2, minus 2, 0. I hope you understand. So we are multiplying 0 times 1 is 0, minus 2 times 0 is 0. So 0 plus 0 is get 0. And then 0 times 0 is 0. Minus 2 times 1 is minus 2. So 0 plus minus 2 gives us minus 2. Minus 2 times 1 is minus 2. 0 times 0 is 0. So minus 2 plus 0 gives us minus 2. Minus 2 times 0 is 0. 0 times 1 is 0. So when you add 0 plus 0, it gives you that. What this implies is this is our I and this is our J. So this is the image of I and this is the image of J. So we can clearly write I, that is I, we have 1, 0, and our J, it is 0, 1. The image, that is our I, is 0, minus 2, and our J prime, or image of J, is minus 2, 0. So we are going to sketch this and see what happens to our unit square, and that is going to help us describe the transformation represented by that matrix. So this is my sketch. This is where I have 1. This is 1. This is where we have minus 1, minus 2. This is 0. This is minus 1. And here we have minus 2. So this is our object and this is our image. We can say that what has happened. Okay, this is where we have our I. This is where we have our K. This is where we have our J. The image of I is 0 minus 2. So this is where we have the image of I. This is where we have our J, minus 2, 0. So this is where we have J prime. Of course, here we have K, the image of K. If we look at this, what has happened to the unit square to give us this image? It has been enlarged, but on the opposite side of the center of origin. This is the center of origin at 0, 0. So when an object is reflected in the opposite side of the center of enlargement, we say that the enlargement factor is minus. The enlargement factor is minus, and if you look at from 0 to I, it is half this. So the distance from the origin to I prime is twice the distance from the origin to the I. So it is enlargement. Enlargement scale factor is equals to minus 2 because it is on the opposite side of the center of the enlargement. Center of enlargement is actually, we can just say center of enlargement is equals to is 0, 0, 0, 0. That is, or we can refer to it as origin. So I think we have seen that it is very easy for using the unit square to give the transformation represented by the matrix. Let's do our final example, and then that will be the end of our lesson. In our last example, find the matrix of refraction in the line y is equals to x. So the line y is equals to x. We can make a sketch of that so that we determine what is a matrix of transformation. This is a sketch. This is a sketch that I have. This we can label it is 1. This is minus 1. This is 0. This is 1. And this is minus 1. Now, because our transformation is a reflection in the line y is equals to x, this is where we can put our I. This is our k. That is our j. So if you reflect I through the line, this of course this is a line y is equals to x. If you reflect this I, the image of I will be here. The image of j will be there. Therefore, the coordinates of I will be 0, minus 1. The coordinates of, that is I prime. The coordinates of j prime are negative 1, 0. Negative 1, 0. And with these two forms a matrix, that is the matrix 0, minus 1, and minus 1, 0. And we can now say this is our I prime and that is our j prime. And remember, we are saying the matrix formed by the image of our unit circle. This is our image, this is our object, forms the matrix of transformation. So the matrix representing the reflection through the line y is equals to x is this matrix, which is now 0, minus 1, minus 1, 0. So that brings us to the end of our lesson. I hope you will be able to get more examples to help you understand in any area that you have not understood. If you have any question, you can always pass it to me. I will be able to assist you. So you are welcome to our third lesson and many more examples that I will be posting. Thank you for listening. Welcome to our fourth lesson in the topic Matrices and Transformation, and this lesson we are going to cover successive transformations. You can transform an object more than one transformation. For example, you can rotate, you can reflect, you can enlarge. So we are going to look at an example here whereby we are going to reflect, rotate, and enlarge. So let's prepare our Cartesian plane. We have this is 0, we have this is 1, 2, 3, 4, 5. So that's our x-axis. Then we have here, we can have 1, 2. We have minus 1, minus 2, minus 3, minus 4, minus 5. And here we can have minus 1, minus 2. So that is, this is y-axis. So we can make our triangle. Let's our triangle start from 1, come to 3, 2, and then we have, so let's say this is our A, this is our B, and this is our C. We are going to join these 3 points to come up with a triangle. So this is our triangle ABC. Our first transformation, we can reflect it through the line y-axis. So our A, this is a line of reflection. Our A will be reflected to this point. Our C will be 3 units from the x-axis, and our B will also be 3 units here. So this is our A, the image of A, this is the image of C, and this is the image of B. So you can give them A prime, B prime, and C prime. So we have obtained our new triangle, A prime, B prime, and C prime, after reflecting our image, our object, to our new image, which we can call image 1, after that transformation. Now we are going to rotate this triangle through an angle of positive 90 degrees. Positive 90, we normally use anti-clockwise direction. So we have here, we can add minus 3. So when you rotate A through an angle of positive 90, we will get our point there. C will come to this point, and our B will be, so this is our A, this is our C, and our B, we have it will be 2 units from C. So this is where we have our B. So we join the 3 points to come up with the second image of the second image after transforming it through a positive of 90 degrees of our first image. We now have our third figure, which is a transformation of the first image. So we have rotated through an angle of 90 degrees, positive 90. So we label this is A double prime, B double prime, and C double prime. So this is our image 2. And then now we are going to do our other transformation, whereby we are going to enlarge this. So our enlargement factor is minus 1.5, and our center of enlargement, let's take 0 and minus 1. So let's see what happens to our second image after we enlarge it through an angle, or through enlargement factor minus 1.5 and center of enlargement 0.0 and minus 1. So this figure will be on the other side of opposite side of our second image. Our new image, after we enlarge this, here is our B for our B apply, and our B not B, our joint points, our now, this is our new triangle. Enlarging image, our new image. So that you understand transformation object of that image, that object. Let us do an example. Form the unit square through matrix A, which is 0, minus 2, minus 2, 0, followed by matrix 1, 0, 0, minus 1, and see what happens. But before we do that, let's call our unit square I. So when you are transforming, we normally follow this order. We say this is our object, and it is followed by, we start by matrix A, followed by B. So that is what the statement means, that we transform our unit square through matrix A, followed by matrix B. So the one that you are starting with is the one next to the image or to the object. So let us transform. We know our first matrix is A, so let's multiply with minus 2, and we have 2. That is a transformation, and our object is 1 0 units square, and since it is a matrix, our image will be 0 is 0, and 2 minus 2 times 0 is 0. 1 will be minus, and we have 0. Actually, it is now. Remember, this is our J, image of R and the image of J. So let's think the unit square. So that is our start origin. Let's say this is our 1. This is our 1. This is Y. This is X. So our unit square will be this. So this is our unit square. So we can say this is have I, we have K, and this is where we have J. After transformation through this, we have our new position of I, which is 0 minus 2. So this is where we have minus 1, minus. So this is where we have our I. Our J is 2 minus 1 minus 0. So this is where we have our J. If you want to know where K is, you just say this is multiply 0, 2 minus 0. You divide by the column vector K, which is minus 2. So minus 2 is minus 2. Minus 2 times 1, that will give 2. So 1 is 0, so the minus 2. So the position K minus 2 is 2. So they have the image. And therefore, that is where we have our first image under the transformation matrix that we have been given 0 minus 2 minus 2 0. So this is our second image. You can call it 2, this is 1. So that we perform successive transformation given those two marks. We are going to example. We could say that is enough for that lesson. So here is another example demonstrating successful transformation, and we are told the following matrix represent various transformations. We have X, we have Y, we have Q, and we have E. A triangle ABC has the vertices A11, B31, and C33. Show on the grid provided triangle ABC and the images and the combined transformation E, Q, Y, X. So this one we read X, Y, Q, E. So if we say this is our triangle, then we say we start with X, we move to Y, we go to Q, and finally we go to E. Before we draw our, we can start by plotting our our triangle. So we have that is the starting point. So we can have 2, 4, 6. So that's our triangle. That's our x-axis. We have 2, we have 4, we have 6. So that's where we have our 6. So this is our y-axis. Then negative side we have -2, -4, -6. So that's our negative side of y. Then we have -2, -4, and -6. Our triangle we are given, first point is at 1, 1. So that's where we have our A. We have our B at 3, 1. So this is where we have 3, 1. So that's how we have B. And C is at 3, 3. 3, 3 is there. So this is our C. So we plot that triangle and see how it looks like. So let's start with the triangle first. That is our object, and we label our axis. So this is 2, this is 4, this is 6. So this is our x-axis. This is 1, this is 2, this is not like that. Let's put this is 2. Of course, this is 0. This is 4. This is 6. That's our y-axis. On the negative side, we have this is -2. This is -4. This is -6. Then the other side, we have -2. -2. We have -4. We have -6. Our triangle is 1, 1. So 1, 1 is there. Our A. Our B is 3, 1. Our 3, 1 is there. So that is our B. Then our C is at 3, 3. So that's our C. So we join the 3 points. That is not the position of C. Our C is at 3, 3. So that's where we have our C. So let's join these points to come up with triangle ABC. So this is our triangle ABC. And then we plot our triangle, the image after transformation. So our A prime is at 1, -1, which is that point. 3, -1 for B. 3, -1. So this is our A. This is our B. And our C is at 3, -3. 3, -3. That is our place for C. So we join these 3 points to come up with our first image. So triangle ABC prime, which you can clearly see it is a reflection through the line x-axis, or y is equals to 0. Now we have another matrix which follows, which is y. So we are going to multiply this matrix by the matrix of our new image. So we have 0. We have -1. We have -1, and we have 0. So we have our matrix, this one, which is 1, -1, 3, -1, 3, -3. So when we multiply that, we find that 0 times 1 is 0, -1 times -1 will be +1. So you will find that this will change. The row will be 1, 1, 3. Then we come to the second row. Then we have -1 times 1 is -1. So generally, you introduce a minus sign to that row. So this will be -1, -3, and -3. So what you need to note here is this will be our second image. So this is A prime, B prime, double prime, and C double prime. So this is our A prime, our first image, B prime, and C prime. So let's go ahead now and plot the image that we have transformed to see how it looks like. Now, here we have 1 minus 1. So 1 minus 1, it means our A double prime will be point of A prime. 1 minus 3 will be there. So our A is here. And this is double prime. Our B double prime is there. I slide it properly. So this is our B. And our C will be at 3 minus 3. So 3 minus 3 is where we have our C prime. So this is our C double prime. So we are going to join the 3 points so that we have the triangle of the second image. So this is our triangle, the second image, which we can clearly see it is a reflection through the line y is equals to minus x, as we had covered. So this is y is equals to minus x. This one was a reflection in the line x-axis, or that is x-axis, or y is equals to 0. The line y is equals to 0. Now, y is equals to 0. Now we go to the third one, which is q, our q here. So we are going to write a matrix q, which is minus 1, 0. We have 0, 1. We mod what we have new here. We have 1 minus 1. We have 1 minus 3. And we have 3 minus 3 is equals to. When you multiply that, it will be 1 minus 1 times 1 is minus 1, and this will be 0. So we will generally introduce a minus sign to that row, which is minus 3. This is minus 3. Then we have 0 times 1, and 1 times minus 1. The row will remain the same, so it is minus, not minus 3, but minus 1, minus 3, minus 3. So that is our figure that we will add image. So we can identify these points. So this is our, now this is our new A, this is our B triple prime, and this is our C. Our A is at minus 1, 1. This is where we have minus 1, 1. So that is where we have our A. 1 minus 1, 3 is at this point. So this is our B, and this is triple prime, and our C is at minus 3, minus 3, minus 3. So that is where we have our C triple prime. We join the 3 points that so that we can be able to see our new image. So now this is our triangle, which we have obtained from the what we have found here. Finally, we go to E. This is our matrix E here. So we are going to write the matrix of E, which is 2, 0, 0, 2. We multiply by our image, which is minus 1, minus 1, minus 1, minus 3, minus 3, minus 3. So when you multiply this, 2 minus 1 is minus 2, 0 times 1 minus 1 is 0. So generally we write minus 2, minus 2, minus 6. The other row, 0 times minus 1 is 0, 2 times minus 1 is minus 2. So we just multiply that by minus 2. So we have minus 2, minus 6, minus 6. This is our final image, which is, we can write it like that. This is my B with 4 marks, and this is our C So we identify this point. Point minus 2, this is where we have minus 2, is somewhere there. Minus 2, minus 6 is there. And minus 6, this is minus 6. This is minus 6, and that is our minus 6. So this is what we have as our image of A. This is where we have our B, and this is where we have our C. So we join the 3 points so that we brought the triangle. So this is our final image which we have obtained, and that has demonstrated clearly what is all about successive transformation, as we have seen. So this is our object. This is our first image. This is our second. This is our third. And this is our final image 4. So I hope you understood what is all about successive transformation. You can look for some questions. You try to work them out like that. Or you can repeat this question and see whether you'll be able to get these objects that we have drawn in this lesson. So that brings us to the end of our lesson. I hope you have understood. If you have any question, you can let me know. Thank you for watching, and welcome to our next lesson. So this is our fifth topic in our topic, matrices and transformation, which is a first from 4 topic. In our today's lesson, we are going to look at inverse of transformation. Okay, let's first of all read this statement. We use a matrix K to transform an object M to M prime. The transformation which maps M prime back to the original object is called inverse transformation, written as K to power minus 1, which is the inverse of K. The product of the two matrices gives you an identity matrix. So let's take an example. Let A represent a positive quarter turn. Then A inverse, which is A to minus 1, represent a negative quarter turn. So this is a positive quarter turn, so the inverse is a negative quarter turn. A, which is a matrix representing positive quarter turn, the matrix is 0, minus 1, 1, and 0. The inverse matrix, that is a negative quarter turn, is represented by 0, 1, negative 1, 0. So what we are saying, if you multiply the two matrices, that is, you multiply the inverse of A, you multiply by A, then this will give you, we start with 0, 1, minus 1, 0. That is A inverse. You multiply by A, which is 0, minus 1, 1, 0. Giving you 0 times 0 is 0, 1 times 1 is 1. So we add 0 plus 1, you get 1. Then we have 0 times minus 1, that is 0. And we have 1 times 0, that will give you 0. So 0 plus 0 is 0. Minus 1 times 0 is 0. 0 times 1 is 0. So here 0 plus 0 is 0. Minus 1 times minus 1 will give you positive 1. So you note that this is an identity matrix. So when you multiply a matrix by its inverse, it gives you an identity matrix. We can also start with A and we multiply by inverse of A. So this is going to give you we start with A, which is 0 minus 1, 1, 0. You multiply by A inverse is 1 minus 1, 0. When you multiply, 0 times 0 is 0, minus 1 times minus 1 will give you positive 1. Then this is 1. Then 0 times 1 is 0, negative 1 times 0 will give you 0. Then we have 1 times 0 is 0, 0 times minus 1 is 0. Then we have 1 times 1 is 1, 0 times 0 is 0, 1 plus 1, 0 is 1. So this is also an identity matrix. So it doesn't matter which one you start with. What we are saying here that when you multiply a matrix, that is the inverse of A you multiply by A, it is equals to A multiplied by inverse of A, which is minus 1, and this to give you an identity matrix. So that is very important, and we are going to do an example to demonstrate this. So this is our example 2, and we are told that triangle PQR has vertices P minus 4 minus 1, Q minus 5 minus 3, and R minus 2 minus 3, and our transformation. The triangle is mapped onto another with the vertices P minus 4 minus 1, Q 5 minus 2, R 2 minus 6. Find the inverse matrix of the transformation. Now, here we need to find the matrix. So first we need to find the matrix of transformation. So let's call our matrix of transformation A, B, C, D. And when you multiply this transformation matrix, we have covered this in our earlier lesson. You multiply by the vertices of a matrix formed by the vertices of our object. This is minus 4, minus 1. This is minus 5. This is minus 3. This is minus 2, minus 3. When you multiply, it should give you the matrix formed by our image, vertices of the image. So this should give you 4 minus 2. Then we have 5 minus 6, and we have 2 minus 6. So when you multiply this, you'll be able to get minus 4 minus 4A minus B. Then we have minus 5A minus 5A minus 3B. Then we have minus 2A minus 3B. We come to the second row. This will give you minus 4C minus D. Then this is minus 5C minus 3D. And finally we have minus 2C minus 3D. So this matrix is equals to our matrix here, which is 4 minus 2, 5 minus 6, and 2 minus 6. Now, here we are going to solve this. We normally say that corresponding elements of the matrix are the same. So we can see here that if we take minus 4A minus B, it should be equals to 4. So, and then we also minus 5A, this is 4A, minus 3B should be equals to our element here, which is 5. These are simultaneous equation, or two linear equation, which we can solve simultaneously. For us to be able to solve this, we need to eliminate 1. So we are going to multiply our equation by, we multiply this by 3 and this by 1. So you end up with minus 12A minus 3B. Then we have it is equals to 4 times 3 is 12. Then the other one will remain the same. 5A minus 3B is equals to 5. Now we should be able to eliminate B by subtraction, so that we have minus 3B minus 3b, that will be 0. So minus 12 minus 5, that will be minus 12a plus 5, and that should give us minus 7. Minus 7a minus 3b minus 3b is 0, and 12 minus 5, that should give us 7. Divide both sides by minus 7, divide by minus 7, and therefore we will have our a. So when you divide through by 7, our a is 1. So we substitute our a in one of this equation here. So we have minus 4 times minus 1, which is the value of a, minus b, it is equals to 4. So this is 4. We take minus b, we take 4, minus 4 times 4 is 4. We take it to the other side, this will be 0. Divide by minus 1, divide by minus 1, then you find it implies that b is equals to actually 0. So once we get b, we can now go ahead and solve the other equation. We use the other, that is, we use 4c minus 4c minus d is equals to minus 2, and minus 5c minus 3d is equals to this is minus 6. We multiply the equation by 3 so that, and 1, so that we are able to eliminate our d, and then we have minus 12c, then we have minus 3d is equals to minus 6, and then we have minus 5c, then we have minus 5c minus 3d is equals to minus 6. So we subtract the second equation from the first equation so that you'll be able to eliminate d and be able to get our c. So we can subtract here, and we will be able to get we subtract now minus 12 c minus 5. This will give you minus 12 plus 5, which is minus 7c. Minus 3 minus 3d will be 0, because it is minus 3 plus 3d, that will give you 0. So this is equals to minus 6 minus 6, that will be minus 6 plus 6, that is 0. So it means 7c minus 7c is equals to 0. Divide both sides by minus 7, you find our c is equals to 0. Now once we find c is 0, we substitute in one of the equation. So we can use minus 4 times 0 minus d is equals to minus 2. Now this will be 0 minus d is equals to minus 2. Divide both sides by minus 1, and then we have our d is equals to, this is minus 1, is equals to actually 2. So we now have found the transformation matrix which we had defined, that A, B, C and D, it is equals to, we have found our A minus 1, our B is 0, our C is 0, and our D is 2. So that is our transformation matrix. Now once you get the transformation matrix, we said that when you multiply the transformation matrix by its inverse, then you should get the identity matrix. So if we write our inverse matrix to be M and WX as our inverse matrix, we multiply by our transformation matrix 0, 2, the product should give us the inverse, the identity matrix, which is 0, 0, 1. So we multiply here, this will be n times minus 1 is minus n, because m times 0 is 0, so here we have minus m. Here we have n times 0 is 0, m times 2 is 2m, so you get 2m, and then we have w times minus 1 is minus w, is 0, so there we end up with minus w, and here we have w times 0 is 0, x times 2, that will give us 2x, and close the bracket, it should give us 1 0 0 1. So this that is our identity matrix. From there you say we equate the corresponding elements. So minus n is equals to 1, so n is equals to minus 1, and then we have m is equals to 0, because 2m is equals to 0. Divide both sides by m. Then our w is equals to 0, and our x is equals to a half. This implies that our transformation matrix is, because we had defined our inverse matrix as n, we have m, we have w, and we have x, and we have found the values of m, n, w, x. So n is equals to minus 1, m is 0, w is 0, and x is a half. So that is the inverse matrix. And since we had said at the beginning that when you multiply the inverse matrix by the transformation matrix, you should get the identity matrix, then we can go ahead. So that's the end. But we can go ahead and show that actually this is the inverse matrix by multiplying the two matrices, that is our transformation matrix and our inverse matrix, and see whether we'll be able to get the identity matrix. So let's see whether we are correct. So we say it is minus 1 0 0 2, that is the transformation matrix. You multiply by minus 1 0 0 and a half, that should give you minus 1 times minus 1, that is 1. 0 times 0 is 0, so 1 plus 0 is 1. Then we have 1 minus 1 times 0 is 0, 0 times a half is 0, so there we have 0. 0 times minus 1 is 0, 0 times 2 times 0 is 0, so we have 0. Then 0 times 0 is 0, 2 times a half is 1. So that is our transformation, that is our identity matrix. So this is the matrix that we got, 0 0 1, which is our identity matrix, which proves that this matrix that obtained here is the inverse of this. So it was a bit lengthy, but I hope you have followed the process, and that is, you can always watch it again, see whether you will be able to follow. From there, we are going to look at the relationship between the area scale factor and the determinant of the transformation matrix. So, in this section, we are going to deal with the relationship between area scale factor and the determinant. In any transformation, the ratio of area of image to area of the object is known as area scale factor. In short, written as ASF, area scale factor. And that is, area scale factor is equals to area of the image divided by the area of the object. The determinant of a matrix is the difference of the product of the elements of main diagonal and the other diagonal. That is, if we are given the matrix A, B, C, and D, determinant product of AD, that is the main diagonal, and minus the product of the elements of the other diagonal. So that is the other diagonal. So that is how we calculate the determinant. Now, from the determinant, so the relationship between the determinant and the area scale factor is that they are numerically equal. The area scale factor is numerically equal to the determinant. Where the determinant is negative, ignore the negative side and take the value to be the determinant, which we are saying that it is equals to the area scale factor. So we are going to do an example and demonstrate that and see whether we will be able to get it clearly. So we have an example here whereby we are told that triangle OAB, whose vertices are 0, 0, and we have A 3, 0, we have B 3, 2, was transformed through the matrix minus 3, 0, 0, minus 3. Find the image area of the area scale factor and show that the determinant is equals to the area scale factor. So this is our transformation matrix, and we pre-multiply with the matrix that is formed from the vertices of our object, and that is 0, 0. We have 3, 0, and we have 3, 2. Close the bracket. It is equals to the matrix that is to be formed using the image vertices. So we have our OAB. Our other matrix we have 0, 0. The matrix formed from the image 0, 0. We have minus 9. We have minus again when you multiply 0 times 3 and minus 3 times 3, we also have minus 9. Then we come to the second row. You have 0 times 0 and minus 3 times 0, we get 0. So the other row we start with 0. Then the other will be 0 times 3 is 0, and minus 3 times 0 is 0, we get 0. And the other one will give us minus 6, that is 0 times 9, 0, minus 3 times 2, you get minus 6. So these are the vertices of our image O prime, A prime, and B prime. So we go ahead and we plot our figures on a Cartesian plane. So here we have the Cartesian, our graph, our grid. We are going to plot. So we start by preparing our Cartesian plane. So we have the x-axis up to number 6, followed by y-axis, and then up to 4. Then we fill the negative side where we have minus 2, minus 4, minus 6, and we have the negative side of x up to minus 9, because the lowest value of x is minus 9. We then identify. We start by our object. So O is at 0, 0. Our A is at 3, 1. So that's where we have our O. Then we go to 3, 1. And our B is at 3, 2. So we join the 3 points to come up with our object. So from there now we plot our image. We have O is at 0, 0. So it lies the same place as the other O, the origin. Our A prime is at minus 9, 0. That's where we have our A prime. And our B prime is at minus 9, minus 6. So that is where we have our B prime. Then once we identify that, we join the 3 points to come up with our image. So we now have our image OAB double prime, and then from there we are required to find the area image, which we have done. We need to find the area scale factor. The area of the image is a half base times height. So that is will give us 2 divided by 2 is 1. So there we have 3. We then get the area of the image, which is a half base times height. That is, we will be able to get a half multiplied by 9 multiplied by 6, and that should give us 9 times 6 would give us 27. 6 divided by 2 is 3, 27. Now from there, area scale factor, we have said it is equals to area of the image divided by area of the object. So it is 27 over 3, and that should give us 9. Then from there we get the determinant of our transformation matrix. Since our transformation matrix is minus 3 times 0, 0 minus 3, it will be minus 3 times minus 3 minus 0 times 0, which should give us 9. So we can clearly see, as we are taught, that the determinant of the matrix is equals to the area scale factor, and that is what we wanted to achieve. So that brings us to the end of that lesson. So after this, we are going to look at another new transformation known as shear, and also another one known as stretch. So you are welcome to our next lesson, which will be finalizing this topic. So thank you for watching. So in this lesson, we are going to run a new transformation known as shear, and we are going to learn about this transformation by studying this diagram. So we have our object in blue, which is O, A, B, and C. So our object is O, A, B, and C. Then we have our image, which is O prime, A prime, B prime, and C prime. So this is a transformation where, so we have our image, it is O prime, A prime, B prime, and C prime. This is a transformation. Our object has been transformed, and the kind of transformation that has happened is known as shear. So how do we describe? We describe shear as follows. This is how we describe shear. OABC is a rectangle, and OABC prime is its image. P and Q are on line OC and AB. So this is our P, this is line OC from there to there, and this is our Q from on line AB. This is our Q. So we can say, and our PQ prime, this is P prime and this is Q prime, are their images. The transformation which maps rectangle OABC on OABC prime is called a shear. And how do we describe this transformation? We describe we have the base height. We have the base, the image, and the object are sharing the same base, that is OA. If you calculate the area of the image and the area of the object, they are the same. So we conclude that the area under shear, the area is invariant. meaning the area of the image and the area of the object are the same. Then each line not parallel to the invariant line intersect with its image in the invariant line, in this case OA. So we are saying OA shared by object and the image. So this is a line that we are calling it, we are calling invariant line. Any other line, for example AB, parallel to the invariant line, AB, this is the object AB and the image AB meet at the invariant line. You can see AB is meeting at 3. You can see OC and OC prime and OC are meeting at O. That is the starting point. So that is the transformation that we call shear. So how do we describe shear? So this is how we describe shear. We mention or we state the invariant line. For example, in this case, our invariant line is O summation, and we also mention one point not on the invariant line and its image. In this case, we can either say we have B, which is at 3, 5. So the coordinates of B, it is transformed to B prime, which is 8, and this is our B prime, 8, 5. So that is how we describe the transformation known as shear. So we are going to do several examples to help us understand this new transformation known as shear. Let's go for the examples. So this is our first example, and we are told to describe the transformation below. So here we have an object OABC, that is in blue, and we have a image OABC prime in purple. And this kind of transformation is what we are referring to as shear. Shear, we have just mentioned that for you to, so we can say the transformation is shear, just like you pull like something elastic, and we have said to describe shear, we describe shear in 2 steps. One, we need to describe the invariant line. Invariant line is the one that does not change or shared by both the object and the image. Our invariant line here is OC. Then the second thing that we use to describe shear is any point which lies in one of the lines which is not parallel to the invariant line. So we can, for example, take A. A is on O, and OA is not parallel to OC. So we can use A and say our original A is at 0,3, changes to or is transformed to our image of A, which is at -2, 3. In this case, you can use one. You can describe any other point, like you can describe also B. B has also moved from 1, 3 to -1, 3, but we only need to describe one point. So that is how you describe that transformation. So our second example, we are still to describe this transformation, and we have our object A, B, C, D, and our image A prime, B prime, C prime, and D prime. So this is a shear. And to describe a shear, transformation, we do it in just 2 points. We look for invariant line. Invariant line is that line which is shared by both the object and the image, and our invariant line in this case is x-axis. X-axis, or y is equals to 0. That is the invariant line. You can see we have said that those lines which are not parallel to the invariant line meet with their object line at the invariant line. So you can see AD, which is the object, meets with AD prime at the invariant line. The same case has happened to AB, and B prime C prime have meet at the invariant line. Then point number 2 that we need to describe the transformation is just pick one point which has been moved. We can either take either B, C, and D, and I'll take like C. C, the point of the object is at 2, 2. It has been transformed to C prime, which is at 4. That is 4, 2. So that is how you describe that transformation, which is a shear. This is our third example. We have been given 2 diagrams here. We have A, B, C, D. Of course, that is the object. We have A prime, B prime, C prime, and D prime, which is the image. So we have said that the lines which are not parallel to the invariant line meet at the invariant line. So we expect AB and AC. Of course, the invariant line lies on the horizontal line. So what we're gonna do here is to extend these lines and see where the two the line AB and A prime meet, and also where CD and CD prime meets. So once we extend this line, they will meet at the line x-axis, or the y is equals to 0. So we can now see that clearly this is a shear. The invariant line is actually line x-axis, or y is equals to 0. That is the invariant line, and we can take any point, one of the point, like we can take B and say B, whose coordinates are 1, 4, has been transformed to B prime, whose coordinates are 3, 4. So that is how we describe the transformation known as shear. So our last example will describe this transformation. Here you can see the line RQ meets with R prime Q prime at the x-axis. So the transformation is a shear. The invariant line is x-axis, and we have the only point that has moved is our R, whose coordinates are 3, 3. It has been transformed to R prime, whose coordinates are 0, 3. So that's how you describe shear transformation, and I hope you have understood. You can go and check for several examples, questions, and work on them. I'll also be posting more questions regarding the shear transformation. Before we wind up, let's have a look at the last example, where we have rectangle PQRS has that vertices P11, Q 2, 1, and 2, 4, and S 1, 4. Shown on a diagram is image under a shear transformation whose matrix is 1, 0, 2, 0. So the first thing is we are going to pre-multiply our transformation matrix. So our transformation matrix is 1, 0. Then we have 2, 1. We multiply by the matrix which we form from the vertices of our rectangle, which is 1, 1, which is 2, 1. We have 2, 4, and we have 1, 4. So when you multiply that, you get the vertices of the image. So this will have multiply 1 times 2 plus 1 times 0 times 1, that will give you 1. 1 times 2, that is 2, 0 times. So generally this will repeat the first row. Then the second one is 2 times 1, that is 2 plus 1 times 1, that will give you 3. The other value should be 5. When you multiply, we have 8, and finally we have 6. This is our P, Q, R, S, and this is our P prime, Q prime, R prime, and S prime. So what remains now is to plot the two figures, and then we'll be able to describe the transformation. So on our grid, let's label our axis. We have that is 0. This is, you can say that is 2. This is 4. This is 6. We have 8. We have 10. Let that be our y-axis. Then the other one, let's have, we can use a different scale. Let's have 1. Then we have 2, 3, 4. I think that is enough. That is our x-axis. Let's start by plotting our image. So our P is there at that is not the position. It is at 1, 1. So this is where we have our P. Our Q is at 2, 1. So this is our Q. Then we have our R is 2, 4. 2, 4, R is there. Then we have our S, which is at 1, 4. That is where we have our S. Let us also identify the points of our image. P is at 3, 1. So 3, 1 is 3, 1. We have no, not 3, 1, but 1, 3. We have 1. This is where we have our 3. So that is where we have our P prime. And then our Q prime is 2, 5. Our Q is 2, 5. 2, 5 is there. That's our Q prime. Then we have our R prime is at 2, 8. This is where we have 2, and that is where we have 8. So this is our R prime. Then we have S is at 1, 6. At 1, 6. So that is where we have our S prime. We are going to join the the points to come up with the figures. So these are the two figures that you get from our calculations here. And we can say if we drop line PS here, it will meet with at PQ, and if we drop RQ, it will meet at Q with R prime. Q prime will meet with RQ at line PQ. So to describe this, we say PQ is the invariant line, and the second way we describe this shear is that we can describe either with P and P P and P, or R. So I will use R. Our R is at 2, 2, 1, and it is mapped onto R prime, which is at 2, 8. So that is how you describe this shear. And that brings us to the end of that lesson under shear. So let's prepare ourselves for the last lesson, which is another transformation known as stretch. So this is our last lesson in the topic matrices and transformation, and in this lesson we are going to look at another transformation known as stretch. So we have a diagram here where we have the object. We have the object is P and Q, R and S. So that's our object. After transformation, then we have our image, which is P. We have Q prime, P prime, Q prime, S prime, and R prime. So this kind of transformation is called a stretch. It is like you have hold the edge SR and stretched it up. So we say in a stretch, we normally have also two ways to describe it. One of them is the invariant line. You can see P and P prime, Q and Q prime are on the same position, meaning that PQ did not change the position, but our SR changed position to S prime and R prime. So that is one description of this transformation. The other one that we use, all the other points have moved in a direction perpendicular to PQ. So we also use the scale factor to describe this transformation. So here we say our image is P S, we divide by PQ. It is also equals to, we also say it is equals to Q prime S prime divide by QS. So this gives you the scale factor. So that is how we describe this kind of transformation. That is the invariant line and the scale factor. So we are going to look at one example and see how it works. So in this example, we are told, using a unit square, find the matrix of a stretch with Roman number 1, x, y, x axis invariant and scale factor 4. Roman number 2, y-axis invariant and scale factor 6. So of course we know the unit square has a matrix 1 0 0 1, whereby this is our y and this is our j. So we are going to plot these 2 points and see the kind of transformation that we have been told here, the description of this transformation. So let's start with Roman number 1. We are told that the unit square x invariant and the scale factor is 4. So we can have our Cartesian plane here, 1, 2, that is our x. Then we have 1, 2, 3, 4. So our unit square is there. So that is where we have this is our j, this is our k, this is our I, and it is the x is invariant. So let's first of all join the 4 points to come up with the unit square. So this is our unit square. Since we are told x-axis is invariant and the stretch is 4, it means from the where we have I, the other one will be 4 units along the y-axis. So we have 2, 3, 4. That is, of course, this is our y. This is where we have our point, and the other one will have it there. So this will be the image of k, will be the image of j, that is j prime. So we join the points to see the transformation that has taken place. So this is the transformation that has happened. We have our object and we have our image. We go to the second transformation, Roman number 2. We are told y-axis invariant and scale factor 6. So we demonstrate that on a Cartesian plane. So this is our grid. So we have our Cartesian plane, that is 0. We have 1, 2, 3, 4, 5, 6, 7. That's our x-axis. Always remember to label. So here 1, 2, 3. So we have our y. Then our unit square. This will be our I. This will be our k. We have covered that in the past lessons, and this is our j. So we are going to join the points to come up with the unit square. So this is our unit square. So it is the transformation y-axis is invariant. So this is invariant, and therefore the k will move along the x-axis. So that is where we have our k. That is the image of k, and I will move to this point. So we join this point to come up with the image. So now we have our image. This is an object up to there. That's where we have, and this is the image. So that is a transformation known as stretch that is described as y is invariant and scale factor is 6. So let's have a look at an isometric and non-isometric transformations. So from stretch, now we look at the isometric and non-isometric transformation. So isometric transformations are those in which the object, that is the object and the image, are congruent. And in this case, what we mean is that the object and the image are of the same size and the same shape. Example of isometric transformation include rotation. When you rotate an object, it doesn't change the shape. It's like you even when you rotate yourself, you rotate, you look at the back, you remain the same person. When you reflect, when you look yourself into the mirror, you don't change. The same case when you reflect an object. And when you translate means changing the position of an object to another position. So that does not change the size, neither does it change the shape. We are going to look at a few examples of isometric and non-isometric. In this case, non-isometric transformation are those transformations whereby the object and the image are not congruent, meaning they are of different size and the shape changes. For example, when we stretch, the shape of the object and the shape of the image are different. When we shear transformation, the shape is different and the size is different. When we enlarge, the object, the image may be bigger or smaller than the object. So those are the ones that are called non-isometric transformation. So let us have a look at a few examples of this kind of situations. So this is our example. We are supposed to identify whether the following matrices represent isometric on an isometric transformation. If you understood the lesson on unit square, you know that when you multiply this matrix with a unit square, it remains the same, because the unit square matrix represent an identity. So if we make a sketch here, we can actually identify that. So this is our y, this is our x. If we assume this is our I and this is our j, you note that I moves to the other side. So this is where we have I prime, and j remains. So we have our image is that. What kind of transformation is this? It is a reflection. So we say we have mentioned up here that reflection is isometric. So this matrix A represent isometric transformation, not isometric transformation. We come to B. What has happened if we make a sketch of our unit square? So this is where we have our unit square. This is I and this is j. Of course, this is 1 and this is 1. Then I has remained its position. So this is where we have I prime, but j has moved 3. Let's assume our 3 is there, and 1. So actually this represents a stretch. So B, we can conclude and say it is non-isometric, because we say a stretch is not isometric. We come to part C. We also make a sketch. You must understand the unit square here very properly. So that is our x, and this is, we are only using the sketch to guide us what type of transformation has happened. So if we say this is our unit square, our image is at 0, 1. So it means our I prime will be there, and the other one will be 1, 0. So this is where we have our j prime. So our unit square will be there. So this is a reflection. It is a reflection. So it is isometric. It is isometric. And finally we got today. We make our sketch here and have our unit square. This is I, this is j. So what has happened to that? Our I remains the same position, that is 1, 0, but j is 0, that is x is 0, and y is 4. This is where we have our new j. So it means this is a stretch where x axis is invariant. This is x and this is our y. X axis is invariant, and the scale factor is actually 4. So this is non-isometric. So that is how we determine using this matrix, and the unit square is assisting us to easily identify. Remember, we have covered that lesson. Easily identify the kind of transformation the matrix represents. So that brings us to the end of our lesson on stretch, and also the end of our topic for topic 1, that is matrices and transformation. So you'll be able to see all those lessons that cover that topic. I'm going to cover another topic. You keep watching.